Good morning, everyone. I'm Jack Brassil. I'm going to be presenting some work that Kyle Jamieson at Princeton and I are doing. You might have heard of this work before. It was initially published in sort of a complete state at SIGCOMM a couple of years back. What we're doing essentially now is working with the University Planning Grant to deploy the system at scale on kind of a showcase project. To get us to that kind of scale confidently, we have to do much more investigation, and I think that's where Cosmos will be able to help us with kind of a medium scale deployment beyond what we've already done, and to explore regimes of operation that we won't really be operating with on campus. So I'll quickly tell you what the project is about. So what's interesting about Princeton campus as a lab projects is control. We own everything, and we own the networks, the ground, the buildings. So it's a great place to do some demonstration of technologies at scale. So that's why we're there. There's a whole bunch of these kind of campus as a lab projects going on at Princeton, several of which I'm involved with. Nick Feemster operates an IoT house, which is a physically standing residential structure on campus that is highly instrumented. There's a vision of about 5 years out, a greenfield deployment of a new lake campus extending the Princeton campus that will be essentially a fully instrumented campus. And what I'm talking about is Wi-Fi access to highly mobile clients on campus. And the best demonstrator that we have available to us is working with the New Jersey Transit Dinky stub from Princeton Junction to the Princeton campus, where we have both control of owning lots of the property along that run next to the train line, so not interfering directly with New Jersey Transit operations, while actually being able to have sort of a portal to campus where visitors arriving to campus will have sort of edge-your-own access and other services on their way into campus even before they technically arrive. Okay, so lots of other applications beyond just the Princeton Dinky. So if you've read this paper in the past, it's an array of cheap small cells, lots of interesting research that I probably won't get into here too much, but again, we're interested in serving mobile clients, sort of speeds up to, car travel through campus types of speeds, but we're going to do it alongside the Dinky line. And, there's a huge number of challenges associated with building out a system at scale. So we're kind of going to go in two directions, which is we'll be looking at sort of research questions, and I think that's exactly the place where Cosmos will be able to help us. And then we're going to explore systems issues of deploying this at scale on, roughly a 2-mile run of the 2.5-mile Dinky line. And the challenges there are systems challenges like how do we power this, how do we do backhaul, how can we make this cheap enough to deploy on campus. We won't be investigating those system challenges in a Cosmos context. In the Cosmos context, we'll be continuing to work on handover algorithms and making the system as efficiently as possible, really just to prevent dense small cells in an urban setting, which would be entirely different from what we'd see on the campus Dinky implementation. So there are lots of tough problems here. I don't want to get into them all, but if you go back and you take a look at sort of the core technology here, the clients driving by multiple access points or associating with multiple access points. We're making use of diversity in both the Uplink and the Downlink by doing lots of packet replication and then managing distributed queues of packets across different access points. We have to do that obviously with very low latency. The existing prototype, which I'll show you in a second, which you would have read about in the paper, does a full implementation of evaluating CSI on every packet upload it to the APs, and then looking at a time window of CSI values to make the determination about how to do handover from AP to AP. In a real system where we have a fixed topology implementation, it probably won't be necessary for us to do that. So if we'd like to do, kind of more work on investigating how we should use that, sort of physical state information in another kind of deployment, that's exactly the kind of work that we'd like to look at in a Cosmos setting. Just some of the major challenges we're facing. The wireless links are obviously highly unpredictable. We have to understand what it looks like to penetrate these actual physical train cars. To do that, we have already experimented at one of the local train stations very early in the morning doing RF penetration testing, and we're actually pleasantly surprised that even though it looks like some of these trains have pretty limited glass, that penetration inside the car from the distances that we're talking about using, sort of normal Wi-Fi power actually looks pretty good. We're really quite pleasantly surprised. Thanks to New Jersey Transit for letting us do that. So again, for downlink, we're pre-buffering at packets that are coming down at multiple APs, and then we're cleaning up afterwards. So let me jump ahead and show you what the current implementation that we have looks like. Again, what I'm not showing you, flipping through these slides, is the large number of sort of technical challenges in synchronizing a system such that this stays performant with vehicles moving. So the original implementation that, this was actually before my time, was making use of 8 APs and a controller in the computer science building at Princeton, cars driving by up to 25 miles per hour. And you can see how handover is working with the different colors between those 8 APs. So we have this basic implementation, phase 1. We're now looking at an implementation in phase 2, which is, again, an actual deployment, order of, 100, 150 APs. But there's some really interesting special characteristics, not just the fixed topology of this, which we'll be able to exploit. So a pretty good example is, powering these APs. How would we do that? It's Princeton property. Technically, we could run power to all these APs. It's a lot of money to do something like that. We already have estimates of spending, upward of $1 million digging for backhaul and power and everything like that, which would be great if we were fully confident about putting together a permanent installation for the foreseeable future for the riders on the Dinky. We're not quite that confident, and that's how Cosmos will help us. So solar power, for example, possible. Trains aren't coming by all the time. We could be shutting down APs and waking them up, kind of just-in-time operation to make the system like this work. We'd like to experiment with wireless backhaul. So we technically, in the past, we've used only exclusively wired backhaul. Wireless backhaul would be another great cost savings on an implementation. Will that work? Will that not work? We don't know, but that's what the project is all about. So, there really are no other technologies that we can easily draw upon to do the kind of fast handovers that we would like to have in a system like this. So there are obviously fast roaming technologies like 11R that we've compared ourselves to in the past. It's actually quite easy on a system that we fully control to do better than some of these existing technologies. Just a couple of things. Here's one comparison of the performance of this system in a small scale versus 11R, TCP download traffic, which is an indication of throughput gains in using a system like this. So we're really looking at moving from a phase 1 system to a phase 2 experiment at scale. To do that large-scale campus experiment, we really need to gain a lot of confidence that it's worth doing the kind of digging and the distribution that we envision for a campus scale network, which would really be a showcase, which would really be something that other departments would be able to sort of exploit to, for example, make announcements to incoming travelers what's going on campus that day. So it's big potential upside for Princeton if we can pull this off. On the other hand, the actual feasibility challenges are, for example, working with New Jersey Transit, who won't always be the easiest potential partner to work with, but they're nonetheless excited about the possibility of doing this. So that's really where we are. So to go from an 8 AP prototype to a 100 plus AP system where we've invested a lot of money in infrastructure really is a challenge. We have lots of problems to investigate. On the other hand, we'd also like to prove in this technology in the sort of urban setting with different kind of client mobility patterns that we envision that Cosmos will be the perfect test bed to do that. So the real challenge for us working with the Cosmos team is how much of our equipment is sort of bring your own kinds of technologies and how much will the Cosmos infrastructure itself be able to provide to allow us to run sort of mid-scale size experiments. So that's the kind of challenges and opportunities available for working with Cosmos. I just want to mention that here's a pointer to the SIGCOMM paper. You can learn more about sort of the technical challenges. We're doing this for real. We're hiring developers to help build out the system in kind of a robust way at scale. It's a potentially large project. So if any of you folks know of people who are interested in doing wireless deployments at scale, please contact us because we're interested in hiring. So I'll stop there. Any questions?